So what we're looking at right here is the three Pythagorean identities. We've already covered them in a previous video, but I'm going to take a moment and prove or show you how these came about. Okay, so the first one I believe we discovered and discussed when we were looking at the first unit circle. Okay, because if you're looking at the unit circle, then this is just x squared plus y squared, or vice versa rather, is equal to 1. So it's Pythagorean theorem. Okay, but if I start with that, and I go ahead and I divide every single term by sine of theta squared, I will get a 1. I will get a cotangent of theta squared, and I will get a cosecant of theta squared, and that is the second Pythagorean identity. Very similarly, if we start back with the original Pythagorean identity, and I divide everything by cosine of theta squared, we will find ourselves at tangent of theta squared plus 1 is equal to secant of theta squared, and that is the other one. Okay. Other identities that we have discussed are even and odd identities, reciprocal identities, quotient identities. I'm going to be doing a lot of toggling in my notes here, so I did put a formula sheet. Basically, these are the ones that we've discovered so far. Okay, and we're going to progress through this unit or chapter. We are going to progress through more of these identities. But first, let's take a peek at what we can do with identities. Ultimately, we're going to end up having to prove or verify trig identities. Before we jump into that, how do we truly know that two things are equal to each other? Well, I am going to show you. I'm going to open up another window here for a second. We're going to look at Desmos here. Okay, I have on the left cotangent of theta and y equals 1 over tangent of theta. Now, it's already on our identity sheet. It's already on our formula sheet. Like, we believe it. We know that it's true, but for full buy-in, you should see a proof for it, right? Well, to first just verify that they're the same, I'm going to graph the cotangent function. And then I'm going to graph 1 over tangent. And we see that 1 over tangent's graphed in blue. 1 over tangent's graphed in blue. And then just the cotangent function is graphed in red. And we can see that they are the exact same thing. Okay, so that is one way to confirm our beliefs that they are the same. Okay, so now I'm going to get rid of that and go here. And we're going to continue to look at how we show it mathematically when two things are equivalent rather than just looking at the graph. So here for this first example, we want to verify that tangent of theta times cosine of theta is equal to sine of theta. Okay, to verify or to prove or to show, it's all asking us the same thing. Manipulate one side of the equation. You can manipulate both. I don't recommend it, but you certainly can. You manipulate until you have the two sides equaling the exact same thing. Here's what I mean by this. For this first example, I know that tangent is equal to sine theta over cosine theta. And then beside that, I have a cosine theta. Well, I know that the cosine on top and a cosine on the bottom are canceling because they're just producing numbers. So the result is that sine theta is equal to, and that's what we wanted to show. We wanted to show that this left side was equal to sine theta. I have done that. I often do a check mark when I have set out what I intended to do. Okay. All right, so let's go to the next one here. Here it says verify the equivalencies, which is that the two sides are equal using even and odd identities. So I'm going to focus my attention on the left side. I'm going to like do some kind of manipulations until I can get it to equal cosine of x squared. Well, I do know that sine is an odd function, so since sine is an odd function, I can rewrite this 1 plus sine x times 1 minus sine x. That's using the odd property, okay? So next I'm going to multiply 1 minus sine x plus sine x minus sine of x squared. Next, simplify 1 minus sine of x squared. And I know that that's a Pythagorean identity, or a manipulation of the Pythagorean identity, and this is equal to cosine of x squared, which is what I was trying to get it to equal. So I have set out to do, or I did what I set out to do. Check. Okay. Now, if you can't or don't see right away that 1 minus sine theta is equal to cosine theta squared is equal to cosine squared, I'll just remind you of the identities that we've established so far. If the Pythagorean identity is sine squared x plus cosine squared x equals 1, and I subtracted a sine squared on both sides, then it's safe to say that cosine squared x is equal to 1 minus sine of x squared, which is what we have. Okay? All right. The next example, we're getting a little bit trickier here. Secant squared minus 1. I think there's many different ways to approach this, and as long as you're not breaking any mathematical rules, there's no wrong answer as far as like what step to do first. So I'm seeing this, I could certainly go, and a lot of instructors will teach you always convert it to sines and cosines. I don't know that that's necessary as a first step here. I might instead try to write it as two fractions and say, oops, I don't want sine, and say secant of theta squared over secant of theta squared minus 1 over secant of theta squared. And I need this to equal sine squared. So these cancel or simplify rather and be 1 minus. Now we know that secant is 1 over cosine. And so I really have 1 over cosine squared. So if I simplify that, it's cosine squared theta. And I do know that 1 minus cosine squared theta is equal to sine of theta squared, which is what I was set out to prove. Okay. Next one says, create an identity for the expression 2 tangent theta secant theta by rewriting strictly in terms of sine. Okay, so they're not telling us what to turn it into specifically. They're just saying, hey, make sure it's got sines in it. So this one is a scenario where I would probably go to sines and cosines. Tangent is sine over cosine times secant, which is 1 over cosine. So I have that. On the top, I have a 2 sine theta. On the bottom, I have a cosine of theta squared, which I do know is 1 minus sine of theta squared, because that's the Pythagorean identity just manipulated. And now this is all in terms of sine, so that's where I'm going to stop. Okay. All right, we're going to just keep doing more examples, and pretty much we're just manipulating those identities that made it to the formula sheet, or the ones that we've discovered so far in class. So we'll use what we know to manipulate and see if we can show that the left and the right are equivalent. Okay, so this one here, I see a lot of negative angles, which kind of tell me that maybe some even and odd business is needed. So keep that in mind. I do know that cosine is even. So this one is even. This one is even. So I can do a rewrite here. I would get sine squared of negative theta. And then cosine is even, so it'll still be a minus sign when I simplify this. Oh, plus it's squared, so, but the theta, the negative theta is not, like, that's the input, don't square that, okay? I'm dropping the negative because of the even function, okay? And then on the bottom, we have a sine of negative theta minus cosine of theta. Now, the top has a difference of squares, so I'm going to factor the top. So first I did even and odd business, and then now I'm going to factor. When I factor the top becomes sine theta plus cosine. Ooh, I have an error. Let's fix it. It's not sine theta, it's sine negative theta plus cosine theta times sine negative theta minus cosine theta over the bottom sine of negative theta minus cosine of theta. I am noticing that this one and this one are the same, okay? And by this bottom one, I mean all of this is the whole thing, okay? The whole thing with the whole thing, and what is left, right, we're simplified, is sine of negative theta minus cosine of theta. What am I doing here? Oh, was that supposed to be a minus? Oh, you know what? I canceled the wrong ones. Let's rewind. Did I? Let's look. I need to take this one out with this one because of the minus signs. All right. So what's left is a sine negative theta plus cosine theta. Now, the sine, this one's odd, so this will be a negative sine. Really, Janine? Of theta plus cosine theta. And honestly, rearranging the order is kind of the least of our worries, but there it is, and now it's equal to what we wanted it to be equal to. You gotta cancel the right things, right? All right, let's keep moving. It's still just manipulations, okay? I think you get the idea. We'll continue this anyway, just to make sure, and then we're gonna get into things that we can do with these, like factor, simplify, or factor, but I'm going to simplify. Okay, so first one more verify, and then we'll move on to other things. You could certainly go to all sines and cosines, or this one, I certainly could multiply it all out. Here's the easier route, okay? If you see it. If you don't see it, you're going to have to multiply it all out and then work on the manipulations. If you do see that there's something you can do to simplify it beforehand, maybe it's in your best interest to do that. Here's what I mean by that. This Pythagorean identity, This is sine of x squared. This one, again, Pythagorean identity. Look at the identities that we've established, or your formula sheet if you have it, is cosecant of x squared. Well, we know that cosecant of x is 1 over sine of x, and it's squared. There's two of them. Those negate each other, and what's left is a 1, which is what we were setting out to show. Okay? All right. Next, here with this number 8, you're going to notice that, well, maybe sometimes you will notice that some of them look algebraic, and so maybe we can manipulate trig functions the same way we would algebra. So to me, when I see this, it looks like 2x squared plus x minus 1. Now, they're not asking us to prove anything or show anything. It's just saying, hey, take a look at this and see if you can see it as an algebraic expression, okay? If you can see it as an algebraic expression, think about what you could do with it. Like, oh, I see that I could factor this. 2x minus 1 and then an x plus 1 will give me the same thing. So was it quadratic? No, this was a trig function, but there was a quadratic kind of component to it. So I know that there really wasn't an x in it, but we could think of it as an x and manipulate it, okay? And why do we want to kind of visually see things that way? Well, I'm going to just keep going with this next example here. Here it says rewrite the expression by factoring the difference of squares. So like if in your head you're thinking, this looks like 4x squared minus 1, and I can factor that into 2x minus 1, 2x plus 1, then without the x's, we could see this as 2 cosine of theta minus 1 times 2 cosine of theta plus 1. So it looks like quadratic in nature, so we can manipulate it by doing the same things we would do as if it was like a quadratic, polynomial. So, all right. And then simplify the expression using identities. So they're not telling us what it should simplify to. They're just saying, hey, simplify it. No problem. I know that, 1, you could change everything to sines and cosines. 2, you don't need to if you can make bigger jumps by using your identities. I do know that I have a Pythagorean identity, and cosecant is equal to 1 plus, cosecant squared, 1 plus cotangent of theta squared, and behind we have a minus cotangent of theta squared. Well, that's quite nice because that means then that we are left with just 1. Okay?